So I want to talk about what looks like, to many people, looks like a fairly straightforward RC circuit. And you think about the circuit and you go, well, this should be a pretty straightforward response. In fact, you look at the two R's and you think to yourself, this looks like a resistor divider at low frequency. That'll make sense. In fact, what we'll find as we do the calculations is that, in fact, we would end up getting a resistor divider. And because the resistors are equal, the gain is going to be a half. And you think that makes sense. And you think to yourself, well, it's an RC type circuit, so I've got a capacitor here. So I just simply say, all right, I probably have a sense of that there's two R's here. Maybe there's a C. The C gets added in somewhere. And I could get some interesting time constant that maybe is related to, I don't know, the parallel combination of the two R's times the sum of the two capacitances. And interestingly enough, if you pick that out as your time constant, that works about right, it turns out. We'll eventually be able to see down here that our core time constant really is sort of the sum of the two capacitances times the parallel combination of the R's. And you think, okay, that's great. And that gives you a very straightforward number of about 2, in this case, it's going to give you 2 milliseconds for your time constant. And you're thinking, okay, so why are you making such a big deal of this circuit, right? Well, imagine that we take a step response and have an input and it goes up and it steps up to 4 volts for this circuit. The response that you would expect, calculate and or measure would be the input would start at 0 because again it's pretty much been 0 for forever, right up to the edge of the step at time equal to 0. Okay. And that's what we would imagine for a very simple function, 4 volt times u of t, right? So right up to 0. And then at t equals 0, what happens? Well, this value jumps up to 3 volts and then converges down to 2 volts. Now, most people would have started with this and said, let me start at 0 and assuming that, well, okay, it's going to go up to 1/2, and 1/2 of 4 volts is 2, so steady state's right. And I would have imagined it just been some exponential increase here. So this is confusing. What happened, right? What happens when you go through the circuit? A couple ways to look at it. A couple ways to look at the circuit. The first thing that you would see is you'd actually sit down and you could write KCL at this node. You get a whole bunch of terms here. That's great. Start working through your terms. Kind of take this element, work through some algebra, group the terms for V out and V in, and you get a transfer function. And you think, great, I have a good transfer function. And you do some reductions and you can see the R2 over R1 plus R2 again, and you're thinking, this is great. And then I have this wonderful transfer function with an S with this time constant underneath plus 1. Everything looks great. I don't have any real concerns, do I? And yet, how did I get there? And you think, okay, she's mistaken. Because, we know that if we were going to look at the value right after t equals 0, what we would do is we would take the structure and we'd say, let me take I would take the limit. If I'm looking at this at t, at that point, I would take t equals 0, I'd take the limit as s goes to infinity, not t goes to infinity. Again, this would also be s goes to infinity here. As s goes to infinity of s v out. And so I would look at the structure, v out over v in, and ask, what do I see? Because that's the response I'm looking for. Well, as s goes to infinity, what term is left? I've got this c1 over c1 plus c2, r1, parallel combinations, all of this drops out. And what I'm left with is that v out over v in is sc1 over s of c1 plus c2. Well, for the values of c1 that I chose here, 3 microfarads and 1 microfarad, this number is 3/4. You think, wait, that's bigger than a half. How did that happen? And it turns out that, yes, indeed, the capacitive divider, it's almost as if the resistors were not there. what you see the capacitor divider is that, in fact, for an input step, it's the capacitor divider that is the primary thing first, and then eventually there's dynamics that eventually lead you back to the resistor divider. So for 3/4, you would expect that a jump of 4 volts puts me up to 3, and then this has a drop down to 2 volts. And it's really important to get a sense that there's both capacitive voltage dividers and resistive voltage dividers in these circuits. And at one time scale, the capacitive type of voltage dividers often will be the key thing, and then the resistive voltage dividers will be the other side of it. This becomes really important. And this circuit is actually really important, I would argue, from a historical perspective, because much of what we understand now about capacitor dividers and the way we think about this in a very elegant way came from a lot of investigations over the years of asking questions of what do I do with floating gate circuits, what do I do with capacitive-based circuits, which are classically you get all in integrated circuits and chips. Because for the most part, until you think about circuits like that, you're like, oh, it's not that important. Things are mostly resistors and in discrete circuits, but it changes. And in particular, this is a circuit that was very important to a colleague of mine in terms of starting his passion for looking at these questions, which actually enabled a lot of passion for many of the rest of us. Because this was basically a very simple circuit in a slightly modified form that that Dr. Middlebrook at Caltech had given to this very, very young graduate student, Brad Minch. And it was an amazing sort of thing because realized that it didn't behave the way he thought it did. And it fascinated him to the point where he kept working and understanding and uncovering so many aspects of circuits. And if you haven't seen his work on any aspect of circuits, I would just highly recommend it. But it turns out it's an amazing how one simple circuit like this has a certain amount of richness to it that you can see in so many different ways and in so many different perspectives.